Hello there. We are about to drift into a place that's closer than your own breath. We're going inside your brain, not with scalpels or scanners, but with curiosity and wonder. Right now, in this very moment, 3 pounds of soft tissue inside your skull is doing something miraculous. It's reading these words. It's creating meaning from symbols. It's holding memories of your entire life while keeping your heart beating without you thinking about it. Your brain is the universe looking back at itself, the cosmos folded into flesh, and somehow, impossibly, it's aware of its own existence. Tonight, we're going to explore this quiet miracle together, and maybe, just maybe, understand a little more about the most mysterious thing in the known universe. If this peaceful journey into science brings you calm, or if you want to discover more fascinating mysteries that help you drift off to sleep, go ahead and hit that like button and subscribe right now. Because tomorrow, I'll be back with another journey into the wonders that surround us. And here's the thing, when you subscribe, you're not just helping this channel grow, you're joining a community of curious minds who love exploring the universe from the comfort of their beds. Also, drop a comment below telling me where in the world you're watching from and what time it is there right now. It's amazing to think that whether it's midnight in New York or dawn in Tokyo, we're all connected by the same sense of wonder. But enough about that. Let yourself sink a little deeper into comfort now. Get cozy. Adjust your pillow. Because we're about to begin a journey inside the most complex structure we know of. And here's what makes this journey special. The brain we're exploring is also the brain doing the exploring. You're using your brain to understand your brain. It's like an eye trying to see itself, or a hand reaching out to touch its own palm. Let me paint you a picture of where we are right now. As you read these words, or hear this voice, billions of tiny cells inside your head are lighting up. They're passing signals to each other faster than you can blink. They're creating the experience of this moment. The feeling of where you're sitting or lying. The sound of your own breathing. The thoughts drifting through your awareness like clouds across a quiet sky. And here's the thing that gets me every single time. Your brain weighs about as much as a small melon. It's soft, wrinkled, pinkish grey. If you could hold it in your hands, it would feel a bit like firm jello. Nothing about it screams miracle at first glance. But this unassuming lump of tissue contains everything you are. Every memory you've ever made. Every dream you've ever had. Every person you've ever loved. Every song that's ever made you cry. It's all in there, somehow, in that 3-pound universe. And right now, as you settle in for this journey, your brain is doing something extraordinary. It's preparing itself for rest. It's already starting to shift gears, moving from the busy speed of daytime thinking into something slower, gentler, more dreamlike. Your brain knows what time it is, even if you've lost track. It has its own clock, ticking away inside, counting the hours and responding to the fading light. So, tonight, we're going to wander through this inner landscape together. We'll discover how thoughts spark like tiny lightning, how memories get stored and reshuffled while you sleep, how your brain cleans itself each night like a faithful caretaker. And we'll do it all slowly, peacefully, with the kind of wonder that helps you drift away Because understanding your brain isn't just about science. It's about understanding yourself. And there's something deeply calming about that. And right now, as you settle in, your brain is doing something extraordinary. It's managing your entire body with a weight that would surprise you. Let's talk about that for a moment. Your brain weighs about 3 pounds. That's it. 3 pounds. About the same as a small cantaloupe you'd pick up at the grocery store. You could hold your entire mind in 2 hands. All your thoughts, your personality, your memories, your ability to recognize your mother's face, or remember the lyrics to your favorite song. 3 pounds. But here's where it gets interesting. Despite being only about 2% of your total body weight, your brain uses roughly 20% of all the energy you consume. 1/5 of everything you eat and drink goes straight to feeding this hungry organ. It's like having a tiny furnace inside your skull, constantly burning fuel to keep the lights on. Think about that for a second. Right now, as you lie there, your brain is working harder than almost any other part of you. And you don't have to do a thing. You don't have to remind your heart to beat. You don't have to schedule your breathing. You don't have to consciously balance your body temperature or tell your stomach to digest your dinner. Your brain handles all of it, quietly, constantly, without bothering you with the details. It's running thousands of operations every single second, monitoring your blood pressure, adjusting your pupils based on the light around you, keeping track of where your limbs are in space so you don't accidentally knock over your water glass, processing sounds from your environment to alert you if something important happens. And it does all this while also letting you think about what you'll have for breakfast tomorrow, or replay a conversation from earlier today, or simply exist in this peaceful moment. Your brain is the ultimate multitasker. And the wild part is, most of what it does happens completely below your awareness. The conscious thoughts you're aware of, the ones that feel like you thinking, those are just the tip of the iceberg. Beneath the surface, your brain is conducting a symphony of activity that would overwhelm you if you had to manage it manually. Imagine if you had to consciously control your breathing every moment of every day. Inhale, exhale, inhale, exhale. You'd never be able to focus on anything else. Or if you had to manually regulate your heartbeat, speeding it up when you climb stairs, slowing it down when you rest. It would be exhausting, but your brain does it all without asking for credit. And it does this work with remarkable efficiency. Compared to a computer, your brain runs on incredibly little power. About 20 watts. That's less than a dim light bulb. Yet, it can do things the most advanced supercomputers still struggle with. Recognizing a friend's face in a crowd. Understanding the emotion behind someone's words. Appreciating the beauty of a sunset. Creating a completely new idea that's never existed before. All of this happens in that 3-pound universe inside your skull. This soft, wrinkled tissue that doesn't look like much is actually the most sophisticated structure in the known cosmos. Scientists have mapped distant galaxies and split atoms and decoded DNA, but your brain remains one of the greatest mysteries we're still trying to solve. And here's something beautiful. Every brain is unique. Yours is different from mine, different from everyone who's ever lived. The exact pattern of connections, the specific memories stored, the particular way you process the world. It's all uniquely you. That 3-pound organ makes you irreplaceable. So as you rest there tonight, give your brain some appreciation. It's been working hard all day, keeping you alive, keeping you thinking, keeping you feeling and experiencing and being human. And soon, very soon, it's going to do something even more remarkable. But here's something even more amazing about all that energy your brain uses. All that energy your brain uses isn't powering some massive engine. It's fueling something far more delicate, something almost impossibly gentle. Every single thought you've ever had, every feeling you've ever felt, every memory you've ever made, all of it happens through tiny electrical signals. Whispers of electricity so faint they would barely light up a firefly. Let me give you some perspective here. The electrical signals in your brain are measured in millivolts. That's 1/1000th of a volt. A standard AA battery produces about 1.5 volts. So the electricity sparking through your neurons right now is hundreds of times weaker than the battery in your TV remote. It's gentler than the static shock you get from touching a doorknob on a dry day. It's quieter than a whisper. And yet, with these tiny sparks, you experience everything. The taste of chocolate melting on your tongue, the feeling of sand between your toes, the sound of rain on a roof, the face of someone you love. All of it, every sensation, every thought, every moment of awareness. It all comes down to these delicate electrical pulses traveling through your brain. You have about 86 billion neurons in your brain. 86 billion tiny cells, each one capable of sending electrical signals. To put that number in perspective, if you tried to count to 86 billion, counting one number every second without stopping, it would take you almost 3,000 years. That's how many neurons are quietly working inside your head right now. Each of these neurons is like a tiny battery, holding a small electrical charge. When a neuron fires, it releases this charge, sending a signal down a long tail called an axon. This signal travels fast, some moving at over 200 miles per hour. Others move slower, more deliberately, taking their time. But all of them are talking, constantly communicating, passing information back and forth like neighbors sharing news over a fence. The conversation never stops. Even right now, as you rest, neurons are firing. They're processing the words you're reading or hearing. They're maintaining your breathing. They're keeping your heart steady. They're holding onto memories and checking your body for anything that needs attention. It's a constant hum of activity, an electrical symphony playing in the dark theater of your skull. And here's what amazes me most. These electrical signals aren't random, they're organized. They follow patterns. When you think about your childhood home, specific neurons light up. When you smell fresh coffee, different neurons respond. When you feel happy or sad or curious or calm, each emotion has its own signature, its own pattern of electrical activity flowing through your brain. Scientists can actually measure these signals. If you've ever seen an EEG, those squiggly lines moving across a screen, that's your brain's electrical activity being recorded. It looks almost like music, waves rising and falling, rhythms overlapping, patterns emerging and dissolving. It's the song of your consciousness, played out in electricity. But you don't need special equipment to know this is happening. you can feel it in a way. When you have a sudden realization, that aha moment, you're feeling the result of thousands of neurons firing in perfect coordination. When a memory pops into your head unexpectedly, that's electrical signals awakening dormant pathways. When you drift off to sleep and your thoughts start to blur and mix in strange ways, that's your brain's electrical patterns shifting, slowing down, preparing for a different kind of work. The electricity in your brain is both powerful and fragile. Powerful enough to create your entire experience of reality. Fragile enough that small changes in chemistry or blood flow can alter everything. A little less oxygen and you feel dizzy. A little shift in certain chemicals and your mood changes. It's a delicate balance, this electrical dance. And your brain maintains it with incredible precision. And those gentle electrical whispers travel along paths more intricate than any roadmap you've ever seen. Those electrical signals don't just jump randomly from one neuron to another. They follow pathways, connections, roads built over years of thinking and learning and experiencing life. And the map of these connections is more complex than anything humans have ever created. Each of your 86 billion neurons connects to other neurons. Not just one or two, thousands. A single neuron can reach out and touch up to 10,000 neighbors. Some connect to even more. They send out branches like trees, reaching towards sunlight, creating a network so dense, so intricate, that if you could see it all at once, it would take your breath away. Let's try to picture this. Imagine a forest, not a small patch of woods, but a vast forest stretching further than you can see. Now, imagine that every single tree in that forest is connected to thousands of other trees by invisible threads. These threads carry messages, passing information from tree to tree, creating a living web of communication. That's what's inside your head right now, a forest of neurons, each one connected to thousands of others, all talking at once. Scientists estimate there are about 100 trillion connections in your brain. 100 trillion. That's more than all the stars in our galaxy. More than all the trees on Earth. More than all the grains of sand on all the beaches you've ever walked on. And every single one of these connections has a purpose. Every single one plays a role in making you who you are. These connections are called synapses. They're the spaces where neurons almost touch, where electrical signals get translated into chemical messages and back into electricity again. And here's what's beautiful about them. They're not fixed. They change. Every time you learn something new, connections strengthen. Every time you repeat an action, pathways get faster. Every time you forget something, connections fade. Your brain is constantly rewiring itself, reshaping this inner forest based on what you pay attention to. Think about the first time you tried to tie your shoes. It was hard, right? Your fingers fumbled. The laces didn't cooperate. Your brain was building new connections, creating a pathway for this new skill. But after tying your shoes hundreds of times, thousands of times, the pathway became a highway. Now you can do it without thinking. That's your neural network at work, turning effort into ease through repetition. The same thing happens with everything you learn. The first time you rode a bike, your brain was frantically building connections, trying to coordinate balance, and steering and pedaling all at once. The first time you read a word, your brain had to link the shape of letters to sounds to meanings. But over time, with practice, these connections became so strong, so automatic, that you don't even notice them anymore. And this network isn't just about skills, it's about everything. Your memories live in patterns of connections. That smell that reminds you of your grandmother's house, it's activating a specific pathway, linking smell to memory to emotion. That song that makes you cry, it's lighting up connections between sound and feeling, and perhaps a specific moment in time. Your brain has woven your entire life into this vast web of connections. What's remarkable is how efficient this system is. Despite having more connections than stars in the Milky Way, your brain manages them all without getting tangled up. Information flows where it needs to go. Memories surface when they're relevant. Skills activate when you need them. It's like a city with trillions of roads, and somehow traffic always flows, messages always arrive, and you never get lost in your own mind. Some pathways in your brain are like major highways. They're used constantly, reinforced through repetition, capable of carrying information at incredible speeds. These are your automatic processes, your deeply ingrained habits, your core memories. Other pathways are like quiet country roads, rarely traveled, but still there, connecting distant parts of your experience in subtle ways. And sometimes, your brain creates brand new connections. This happens when you have a sudden insight, when two ideas that seemed unrelated suddenly click together. It's like discovering a shortcut through the forest, a new path that was always possible, but never explored until that moment. Creativity lives in these new connections, these novel pathways your brain builds when it combines things in ways it never has before. But this vast forest inside your head does something remarkable while you sleep. While you sleep, while your conscious mind drifts through dreams or settles into darkness, your brain doesn't rest. Not really. Instead, it starts one of its most important jobs. It cleans itself. And the way it does this is nothing short of amazing. Your brain has its own cleaning system called the glymphatic system. Scientists only discovered it relatively recently, which is wild when you think about it. We've mapped distant planets and sequenced the human genome, but we only figured out how the brain takes out its trash in the last couple decades. And it turns out, this cleaning happens mostly while you sleep. Here's how it works. During the day, while you're awake and active, your brain cells are packed together pretty tightly. They're busy processing information, sending signals, keeping you conscious and aware. But when you fall asleep, something remarkable happens. Your brain cells actually shrink. Not by much, but enough. They shrink by about 60%, creating space between them. Think of it like a crowded city during rush hour. Everyone's packed together, shoulder to shoulder, moving through tight spaces. But then night falls, people go home, and suddenly there's room to move. The streets open up. That's what happens in your brain when you sleep. The cells pull back, creating channels, little rivers of space between them. And into these spaces flows fluid, cerebrospinal fluid, the clear liquid that surrounds your brain, spinal cord. During the day, this fluid mostly stays on the outside, cushioning your brain, protecting it from bumps and jolts. But at night, it gets a different job. It becomes the cleaning crew. This fluid flows through the spaces between your brain cells, like water flowing through a stream bed. And as it flows, it picks things up. All day long, as your neurons fire and work and keep you thinking, they produce waste. Little bits of proteins, byproducts of all that electrical activity, cellular debris. During the day, this waste builds up. There's no time to clean it properly. The brain is too busy doing other things. But at night, the fluid washes through, collecting all this waste, carrying it away. It's like a gentle tide coming in to clean a beach, picking up debris and carrying it out to sea. The waste gets flushed out of your brain, eventually making its way into your bloodstream, where your body can process it and get rid of it. This is one of the reasons why sleep feels so refreshing. You're literally cleaning your brain. All the mental clutter from the day, the waste products of thinking and being conscious, they get washed away while you sleep. You wake up with a cleaner brain, ready to make new connections, store new memories, process new experiences. And here's something important. This cleaning process doesn't work as well if you don't sleep enough. If you cut your sleep short, your brain doesn't get enough time to flush out all the waste. It's like only half cleaning your house. Sure, it looks okay, but the dirt is still there, building up, waiting to cause problems later. Scientists think this cleaning process might be connected to all sorts of things. Memory problems, mental fog, even diseases that affect the brain as we age. When waste builds up over time because the cleaning system isn't working properly, it can cause damage. It's like leaving garbage on the street instead of taking it out. Eventually, it becomes a problem. But when you do sleep well, when you give your brain the time it needs, this system works beautifully. The cells shrink back, the fluid flows through, the waste gets carried away. It's a nightly restoration, a reset button that prepares your brain for another day of thinking and feeling and experiencing the world. And the beautiful thing is, you don't have to do anything. You don't have to think about it, or manage it, or worry about whether it's happening correctly. You just have to sleep. Your brain takes care of the rest. It knows what to do. It's been doing this every night of your entire life, quietly maintaining itself, keeping things clean and functional. Right now, as you lie there reading or listening to this, your brain is already preparing for this nightly cleaning. It's sensing the time, noticing the dimming light or the quiet around you, starting to shift into its nighttime mode. Soon, those cells will shrink back, the fluid will begin to flow, and the cleaning will start. And while this cleaning happens, your brain is also busy doing something else. While your brain cleans itself, while fluid flows through those spaces between cells, something else is happening. Something strange and wonderful and still mysterious. You're dreaming, or you will be soon. And dreams are your brain's way of organizing the chaos of being alive. Most of your dreaming happens during a phase of sleep called REM sleep. REM stands for rapid eye movement, because during this phase, your eyes dart back and forth beneath your closed lids, as if watching something. And in a way, they are. They're watching the movie your brain is creating, the strange theater of dreams playing out in the darkness. During REM sleep, your brain becomes incredibly active. In fact, some parts of your brain are just as active during REM sleep as they are when you're wide awake. If someone were monitoring your brainwaves, they'd see patterns that look almost identical to waking consciousness. But you're not awake. You're somewhere else entirely. Wandering through landscapes that don't exist, talking to people who aren't there, experiencing things that couldn't possibly happen. Your brain uses this time to process everything that happened during the day. All the experiences you had, the conversations you heard, the things you learned, the emotions you felt. It sorts through them like someone organizing a messy desk, deciding what's important, what should be remembered, what can be forgotten. Think of your brain as having a filing cabinet. During the day, papers get scattered everywhere. Notes pile up. Things get shoved into random drawers just to get them out of the way. But at night, during dreams, your brain goes through all those papers. It decides which ones belong in permanent files, which ones can be recycled, which ones need to be connected to other information you already have stored away. This is why dreams often feel so strange. Your brain is making connections, linking new experiences to old memories, trying to find patterns and meaning. It pulls out a memory from childhood and mixes it with something that happened yesterday. It combines your childhood home with your current workplace. It puts your third grade teacher in a conversation with your best friend. None of it makes logical sense, but that's not the point. Your brain isn't trying to be logical. It's trying to integrate information. Scientists still don't fully understand why dreams are so bizarre. Why we can fly in dreams, or breathe underwater, or talk to people who've been gone for years. Why the laws of physics don't apply. Why time jumps around. Why we accept the strangest things as perfectly normal until we wake up. And honestly, there's something beautiful about that mystery. Some things about the brain, about consciousness itself, still resist explanation. What we do know is that dreaming seems to help with emotional processing. If you go through something difficult during the day, your brain often works through it at night in dreams. It's like your mind is trying on different perspectives, exploring different outcomes, helping you make sense of feelings that might be too big to process while you're awake. This is why people often say to sleep on it when facing a tough decision. Your brain literally continues working on the problem while you sleep. Dreams also seem to help with learning. If you practice a new skill during the day, your brain replays it at night, strengthening those neural connections we talked about earlier. Musicians dream about playing their instruments. Athletes dream about their sport. Students dream about what they studied. Your brain is rehearsing, solidifying the pathways, turning new information into lasting knowledge. And sometimes, dreams give us creative insights. There are famous stories of scientists and artists who solved problems in their dreams. They went to bed, stuck on something, and woke up with the answer. This happens because dreaming allows your brain to make unusual connections, to link ideas in ways you might never consider while awake. It's like your brain has permission to be weird, to try combinations that don't seem to make sense. And sometimes those strange combinations lead to brilliant ideas. Most nights, you cycle through several periods of REM sleep, each one lasting longer than the one before. The first REM period might last only 10 minutes, but by morning, you might be in REM sleep for 30 minutes or more. This is why your most vivid dreams often happen right before you wake up. Your brain has been building up to them all night, getting deeper and deeper into its sorting and processing work. You might not remember most of your dreams. In fact, you probably forget the majority of them within minutes of waking up. But that doesn't mean they weren't important. The work happened whether you remember it or not. Your brain sorted through the filing cabinet, made its connections, processed its emotions, all in the strange theatre of dreams. But even when you're not dreaming, your brain is storing something precious. Whether you're dreaming or awake, your brain is constantly storing memories, building a library of everything you've experienced. And the way it does this is more intricate and more beautiful than any library you've ever walked into. There's a part of your brain called the hippocampus. It's tucked deep inside, shaped like a seahorse, which is actually what hippocampus means in Greek. This little structure, about the size of your thumb, acts as the librarian of your brain. When something happens to you, when you experience a moment worth remembering, the hippocampus is the one who decides whether it gets filed away or forgotten. But here's the interesting part. The hippocampus doesn't actually store the memories itself. It's more like a coordinator, a cataloger. When you experience something, different aspects of that experience get processed in different parts of your brain. The sights go to your visual cortex. The sounds go to your auditory cortex. The emotions go to your amygdala. The physical sensations go to your sensory areas. Your memory of any single moment is scattered across your brain, like stars scattered across the sky. The hippocampus links all these scattered pieces together. It creates a map, a set of connections that says, these pieces belong together. They're all part of the same memory. So, when you remember your 10th birthday party, you're not pulling out a single file from a single drawer. You're activating connections across your entire brain, bringing together the image of the cake, the sound of people singing, the feeling of excitement, the smell of candles being blown out. And here's something fascinating. Every time you remember something, you don't just replay it like a video. You recreate it. Your brain rebuilds the memory from all those scattered pieces, pulling them back together into something that feels whole. But in the process of rebuilding, tiny changes can happen. Details shift. Colors might be slightly different than they actually were. Words might change a little. The memory gets subtly rewritten each time you access it. This is why your oldest memories are often more story than fact. You've remembered them so many times, rebuilt them so many times, that they've changed shape over the years. Like a story told and retold around a campfire, the basic structure remains, but the details have been smoothed and polished and altered by time. That doesn't make them less precious. If anything, it makes them more human. Your brain is constantly deciding what's worth remembering and what can be let go. Most of what happens to you in any given day fades away. You don't remember every step you took, every breath you breathed, every moment you existed. That would be overwhelming, impossible to manage. So your brain filters. It keeps what seems important and releases the rest. Emotional experiences tend to stick better. This is why you remember your first day of school, your first kiss, moments of grief or joy or fear. Strong emotions signal to your brain that something important is happening, something worth storing. The hippocampus pays extra attention, makes stronger connections, ensures those memories get filed carefully. Repetition also helps. This is why you remember your childhood home in such detail. You lived there day after day, walking the same halls, seeing the same rooms. Each repetition strengthened the connections, built the pathways deeper and deeper, until that memory became a permanent part of your brain's architecture. But memories don't all get treated equally. Some are crystal clear, vivid and detailed. Others are hazy, more like impressions than actual recollections. Some memories you can recall voluntarily, pulling them up whenever you want. Others only surface unexpectedly, triggered by a smell or a song or a random thought. Your brain categorizes memories in different ways, stores them with different levels of detail, gives them different priorities. And memories aren't static. They interact with each other. New experiences color old memories. Old memories influence how you interpret new experiences. Your brain is constantly weaving connections between past and present, building a narrative of your life that makes sense to you. This is why two people can experience the same event and remember it completely differently. Each brain is building its own story, emphasizing different details, making different connections. The hippocampus works especially hard during sleep, which is another reason sleep is so important. While you're resting, it's consolidating the day's experiences, deciding what stays and what goes, strengthening the connections that matter. This is why studying before bed can be effective, why sleeping after learning something helps you remember it better. Your brain uses that quiet time to cement new information into long-term storage. And some of these memories your brain holds onto, without you even trying. Some memories in your brain don't require any effort to recall. They just happen. Without thinking, without trying, you know how to do things. This is a different kind of memory entirely, stored in a different place, working in a different way. When you ride a bike, you don't consciously think about balancing or pedaling or steering. You just do it. Your body knows. Your brain has stored this knowledge so deeply that it feels like instinct. This kind of memory is called procedural memory, and it lives in parts of your brain that work mostly without your awareness. The main storage center for these automatic skills is a structure called the cerebellum, tucked at the back and bottom of your brain. It's wrinkled and dense, packed with more neurons than the rest of your brain combined, despite being much smaller. The cerebellum is all about coordination, timing, and learned movements. It's the reason you can walk without consciously lifting each foot, type without looking at your fingers, catch a ball without calculating its trajectory. Think about tying your shoes. The first time you learned, it was hard. You had to focus on every loop, every pull, every twist of the laces. Your conscious mind was fully engaged, working through each step deliberately. But now, years later, your hands just know what to do. The memory has moved from conscious effort to automatic action. It's been handed over to the cerebellum, filed away in a part of your brain that runs on autopilot. This is your brain being efficient. Every skill that becomes automatic frees up space in your conscious mind for other things. If you had to think about every single action you perform, you'd be mentally exhausted within an hour. But because your brain can automate repeated tasks, you can walk and talk at the same time. You can drive a familiar route while thinking about something completely different. You can brush your teeth while planning your day. These procedural memories are incredibly stable. You might forget someone's name, lose track of what you had for lunch last Tuesday, struggle to recall the plot of a movie you watched last year. But the skills you learned years ago stay with you. People talk about muscle memory, but it's not really the muscles remembering. It's your brain, holding onto these patterns so firmly that they feel like part of your body itself. This is why the phrase, "it's like riding a bike," exists. Even if you haven't ridden a bicycle in 20 years, your brain still knows how. The connections are still there, dormant but intact. The moment you get back on, those pathways light up again, and your body remembers. Your brain saves energy by making repeated actions automatic. Every routine you have, every habit you've built, it's your brain trying to conserve resources. The neural pathways for these actions become like well-worn trails through a forest, easy to follow, requiring minimal effort. Your brain loves patterns and routines because they're efficient. And these automatic memories extend beyond physical skills. The route you drive to work becomes automatic. The way you organize your morning routine becomes automatic. Even certain thought patterns can become habitual. Neural pathways. You travel so often they feel like the only way to think. But your brain doesn't just remember actions, it remembers feelings too. Deep in your brain, nestled in a region called the limbic system, sits a small structure shaped like an almond. It's called the amygdala, and it's your emotional compass. This tiny piece of tissue, no bigger than the nut it's named after, plays an enormous role in how you feel about the world. The amygdala is always scanning, always watching, always asking one basic question: is this safe or dangerous? It processes emotions faster than your conscious mind can keep up. Before you even realize you're scared, your amygdala has already detected the threat and started preparing your body to respond. Before you know you're happy, it's already registered the pleasant stimulus and begun releasing the signals that create that feeling of joy. This is your brain's early warning system. It developed over millions of years of evolution, designed to keep our ancestors alive. When they encountered a predator, they didn't have time to think through their options. The amygdala handled it instantly, flooding their body with fear and adrenaline, preparing them to fight or run. That same system is still working in you today, even though the threats you face are usually very different. Your amygdala doesn't just detect threats, it processes all emotions. Happiness, sadness, anger, disgust, surprise, fear. It helps you read emotions in other people too. When you look at someone's face and instantly know they're upset, that's your amygdala at work. It's reading subtle cues in their expression, comparing them to patterns it's learned over your lifetime, and delivering an instant assessment. And here's something beautiful about how this works. Your amygdala is deeply connected to your hippocampus, that memory center we talked about earlier. This is why emotions and memories are so intertwined. Strong emotions signal to your brain that something important is happening, something worth remembering. The amygdala essentially tells the hippocampus, pay attention to this, store this carefully, this matters. This is why you remember emotional moments so vividly. Your first day of school, a wedding, a loss, a moment of pure joy. The emotional intensity stamps these memories into your brain with extra detail, extra color, extra permanence. Years later, you might forget what you had for breakfast last Tuesday, but you'll remember exactly where you were when something deeply emotional happened. Your amygdala also learns from experience. If something scared you once, it remembers. This is why phobias can develop from a single bad experience. Your amygdala creates an association between the stimulus and the danger, and from then on, it reacts with fear whenever it encounters that stimulus again. It's trying to protect you, even if the original threat no longer exists. But the amygdala isn't just about negative emotions. It lights up during positive experiences too. When you see someone you love, when you taste something delicious, when you hear music that moves you, your amygdala is part of that response. It's helping you recognize pleasure, safety, connection. As you rest here now, your amygdala is calm. It's sensing the safety of this moment, the quiet, the stillness. It's not detecting any threats, not sounding any alarms. This allows the rest of your brain to relax, to drift, to prepare for sleep. And this emotional center connects to something that makes you uniquely you. Right behind your forehead, sitting at the very front of your brain, is a region called the prefrontal cortex. If your brain is an orchestra, this is the conductor. It's the part that makes plans, weighs options, imagines futures that don't exist yet. It's the part that makes you most consciously you. This region is responsible for what scientists call executive function. That's a fancy way of saying it helps you do complex thinking. When you decide what to have for dinner, that's your prefrontal cortex comparing options. When you resist the urge to say something you might regret, that's your prefrontal cortex applying the brakes. When you imagine what your life might look like 5 years from now, that's your prefrontal cortex traveling through time. Your prefrontal cortex is also where your personality lives, in a sense. It influences how you interact with the world, how you make decisions, what kind of person you choose to be. Damage to this area can actually change someone's personality, which tells us just how important it is to who we are. Here's something interesting. This part of your brain develops last. While most of your brain is fully formed by the time you're a young child, the prefrontal cortex continues developing well into your 20s. Some research suggests it's not fully mature until around age 25. This is why teenagers and young adults sometimes struggle with impulse control, long-term planning, and risk assessment. Their prefrontal cortex is still under construction, but once it's fully developed, this region becomes incredibly sophisticated. It can hold multiple ideas in mind at once, comparing and contrasting them. It can override emotional impulses from the amygdala, helping you stay calm when you want to panic. It can create detailed plans for the future, breaking big goals down into smaller steps. The prefrontal cortex is also involved in social behavior. It helps you understand social rules, read social situations, adjust your behavior based on context. This is why you act differently at a job interview than you do with close friends. Your prefrontal cortex is constantly monitoring the social environment and adjusting your responses accordingly. And it works closely with your working memory, that temporary storage space where you hold information you're currently using. When you're trying to solve a problem, following directions, or having a conversation, your prefrontal cortex is juggling all the relevant information, keeping track of what's important, filtering out what's not. But here's the thing about the prefrontal cortex. It's energy hungry and easily tired. This is why decision fatigue is real. After making lots of decisions, this part of your brain gets exhausted. It's why you might make worse choices at the end of a long day. Your conductor is tired, and the orchestra starts to lose its coordination. This is also why sleep is so crucial for good decision-making. When you're well rested, your prefrontal cortex works at its best. You can think clearly, plan effectively, control your impulses. But when you're sleep-deprived, this region struggles. You become more impulsive, less able to focus, worse at planning. Right now, as you prepare for sleep, your prefrontal cortex is starting to quiet down. It's releasing its tight control, letting other parts of your brain take over. This is part of why your thoughts get dreamy and loose as you drift off. The conductor is stepping down, and the orchestra is beginning to play without direction. But this conductor doesn't work alone. It needs constant communication from another part. Your prefrontal cortex needs information to make decisions, and much of that information comes from a strip of brain tissue that runs like a headband from ear to ear across the top of your head. This is your sensory cortex, and it's constantly translating everything your body feels into signals your brain can understand. Every sensation you experience in your body has a corresponding spot in this region. Touch your fingertip to your nose, and specific neurons in your sensory cortex light up. Wiggle your toes, and different neurons respond. Feel the fabric of your clothes against your skin, and yet another pattern activates. Your entire body is mapped out across this strip of brain tissue. But here's what's fascinating about this map. It's not proportional. The areas of your body that are most sensitive get more brain space devoted to them. Your hands, especially your fingertips, take up a huge portion of the sensory cortex. Your lips and tongue also get an enormous amount of space. Meanwhile, your back, which is much larger in actual size, gets relatively little brain real estate. Scientists have created drawings of what a human would look like if our body matched the proportions of our sensory cortex. They call it a sensory homunculus. It's a strange-looking figure with gigantic hands, huge lips, a massive tongue, and a relatively tiny torso and legs. It looks bizarre, but it perfectly represents how much brain power we dedicate to different body parts. This makes sense when you think about it. Your hands need to be sensitive because you use them to interact with the world in precise ways. Your lips and tongue need detailed sensing for eating and speaking. These parts need more processing power, more neurons dedicated to interpreting their signals, because the information they provide is so important. Your sensory cortex doesn't just handle touch, it processes temperature too. Right now, you can probably feel the temperature of the air around you without thinking about it. Maybe there's a cool breeze, or maybe the room feels warm. Your skin is covered in sensors that detect temperature changes, and those signals get translated in your sensory cortex into the experience of hot or cold. Pain also gets processed here, though it's more complex than other sensations. Pain involves multiple brain regions working together, including emotional centers like the amygdala. This is why pain isn't just physical. It has an emotional component too. The same injury can hurt more when you're stressed or scared, less when you're calm or distracted. Your brain is always interpreting pain in context, deciding how much attention it deserves. And all of these sensations, every touch and temperature and twinge, get integrated with information from your other senses. Your brain is constantly building a complete picture of your physical experience, combining what you feel with what you see and hear and smell. This gives you a coherent sense of being in a body, of existing in physical space. Right now, your sensory cortex is registering the surface beneath you, the pillow under your head, the weight of blankets, the temperature of the room. It's all being processed, translated, understood. And this map is constantly updating based on what you experience. That map in your sensory cortex isn't fixed. It changes. In fact, your entire brain changes, constantly reshaping itself based on what you do, what you learn, what you pay attention to. Scientists call this neuroplasticity, and it's one of the most hopeful things about being human. Your brain is plastic, not like a plastic toy, but plastic in the original sense of the word, meaning moldable, changeable, capable of taking new forms. Every experience you have literally changes your brain's physical structure. New connections form between neurons. Existing connections get stronger or weaker. Some pathways become highways, while others fade into overgrown trails. When you learn to play an instrument, the areas of your brain responsible for finger movement expand. Musicians who play string instruments have larger representations of their left hand in their sensory cortex, because those fingers need to move with such precision. The brain dedicates more space to what you use most. Taxi drivers in London who spend years memorizing the city's complicated street layout develop larger hippocampi. That memory center we talked about earlier actually grows in response to the demands placed on it. The brain builds more neural real estate when you need it. Even learning a new language changes your brain structure. The areas involved in language processing become more densely connected. Your brain is literally rewiring itself to accommodate new words, new grammar, new ways of expressing thought. And this doesn't just happen when you're young. For a long time, scientists believed the brain stopped changing after childhood. They thought adult brains were fixed, unable to form new connections or adapt to new situations. But we now know that's not true. Your brain remains plastic throughout your entire life. It's always capable of change. This means you're literally not the same person you were yesterday. Every conversation you had, every sight you saw, every thought you thought, it all left traces in your brain. Tiny physical changes, new connections forming, old ones adjusting. You are constantly being remade by your experiences. This is incredibly hopeful for people recovering from brain injuries. The brain can sometimes root around damage, forming new pathways to restore lost functions. It takes time and effort, but the brain's plasticity makes recovery possible in ways that wouldn't be if our neural connections were fixed. It also means you can always learn new things. The old saying about not being able to teach an old dog new tricks doesn't apply to human brains. Yes, learning might take more effort as you age. Yes, children's brains are especially plastic during certain developmental windows. But your brain never loses its ability to change and grow. The key is engagement. Your brain changes most in response to activities that challenge it, that require attention and effort. Passive activities don't reshape your brain as much, but when you actively engage with something new, when you struggle a bit, when you practice and improve, that's when your brain builds new connections most effectively. Sleep plays a crucial role in this process too. Those new connections you form during the day get strengthened and consolidated while you sleep. This is your brain cementing new learning into place, making temporary changes permanent. And this ability to change is most powerful during certain times. There are certain times in life when your brain is especially hungry to learn. Scientists call these critical periods, windows of time when your brain is primed to absorb specific types of information with unusual ease. And while these windows are most dramatic in childhood, your brain never completely closes them. Think about language. Children can learn multiple languages simultaneously without even trying. They absorb grammar rules they've never been taught, pick up accents perfectly, switch between languages effortlessly. Their brains are in a critical period for language acquisition, soaking up linguistic information like sponges. This doesn't mean adults can't learn new languages. They absolutely can, but it requires more conscious effort, more deliberate practice. The window is narrower, but it's not closed. Your brain is still capable of forming the neural pathways needed for a new language. It just has to work a bit harder to do it. The same applies to music. Children who start learning instruments young often develop perfect pitch, the ability to identify or produce any musical note without a reference. This skill is nearly impossible to develop if you start learning music as an adult. The critical period for perfect pitch closes relatively early, but adults can still become excellent musicians, still learn to play beautifully, still develop deep musical understanding. Your brain's plasticity is highest when you're young, but it never disappears entirely. What changes is how easy it is to form new connections. Children's brains form new synapses at an incredible rate, building neural pathways rapidly. Adult brains are more selective, more careful about which connections to strengthen. But here's something wonderful. While children's brains might form connections faster, adult brains are better at connecting new information to existing knowledge. Adults have years of experience to draw on, frameworks for understanding that children don't have yet. This makes certain types of learning actually easier as you age. And sleep is crucial for all of this learning at every age. When you learn something new during the day, the initial memory is fragile. It's like a path through grass that someone has walked once. Sleep is what turns that faint trail into a lasting pathway. During sleep, your brain replays what you learned, not consciously, but at a neural level. The same patterns of brain activity that fired when you first learned something fire again while you sleep. Each replay strengthens the connections a little more. By morning, what was new and uncertain has become more solid, more integrated into your existing knowledge. This is why studying before bed can be so effective. You give your brain new information, then immediately give it the sleep time it needs to process and store that information. It's like planting seeds and then watering them right away. Athletes use this too, often without realizing it. When you practice a physical skill, your brain is learning movement patterns. During sleep, those patterns get reinforced. You can literally get better at a sport while you're lying in bed, not moving at all, because your brain is strengthening the neural pathways that control those movements. The same happens with problem solving. You've probably experienced going to bed stuck on a problem and waking up with the solution. Your brain continued working on it while you slept, making connections you couldn't see while awake. But learning isn't the only thing that changes your brain. Your brain doesn't just work through electricity, it also works through chemistry. Inside your head right now, there's a complex pharmacy of chemicals being created, released, and absorbed. These chemicals, called neurotransmitters, influence everything from your mood to your motivation to your ability to feel pleasure. Think of neurotransmitters as chemical messengers. When an electrical signal reaches the end of a neuron, it triggers the release of these chemicals. They float across the tiny gap between neurons and attach to receptors on the other side, passing the message along. Different neurotransmitters create different effects, influencing how you feel and how you think. Serotonin is one you've probably heard of. It plays a big role in mood regulation, helping you feel calm and content. When serotonin levels are balanced, the world feels manageable. When they're low, everything can seem darker, harder. Many antidepressant medications work by increasing the availability of serotonin in your brain. Dopamine is another major player. It's often called the reward chemical because it surges when you experience something pleasurable or achieve a goal. That feeling of satisfaction when you complete a task. That rush of happiness when something good happens. That's dopamine at work. It motivates you to seek rewards, to pursue goals, to keep trying. Your brain releases dopamine not just when you get a reward, but also in anticipation of one. This is why looking forward to something can feel almost as good as the thing itself. Your brain is already releasing dopamine in response to the expected pleasure. Endorphins are your brain's natural pain relievers. They're released during exercise, which is why people talk about a runner's high. They're also released during laughter, which might explain why laughing can actually make you feel physically better. Your brain has its own pharmacy of feel-good chemicals. No prescription needed. Then there's GABA, which works like a brake pedal for your brain. It slows down neural activity, creating calm and relaxation. Without enough GABA, your brain can get overstimulated, leading to anxiety. With the right balance, you feel peaceful and centered. These chemicals don't work in isolation. They interact with each other in complex ways, creating the full spectrum of human emotion. Your mood at any given moment is the result of this intricate chemical dance happening across billions of neurons. And your daily habits influence this chemistry. Exercise increases endorphins and dopamine. Sunlight helps regulate serotonin production. Good sleep helps maintain the balance of all these chemicals. Poor sleep disrupts it. This is why, when you're sleep deprived, your mood suffers. The chemistry gets out of balance. What you eat matters too. Your brain needs specific nutrients to produce these neurotransmitters. Proteins provide the building blocks. Certain vitamins and minerals act as helpers in the production process. Your brain is literally creating its mood chemicals from the food you consume. Right now, as you rest, your brain is working to restore chemical balance. The stress hormones from the day are fading. Calming neurotransmitters are increasing. Your brain is preparing its chemical environment for sleep, adjusting levels to help you drift off peacefully. And these chemicals flow through spaces smaller than you can imagine. All of those neurotransmitters we just talked about, all those chemical messages, they cross a space so small you need a powerful microscope to see it. This space is called a synapse, and it's where the real magic of your brain happens. Neurons don't actually touch each other. There's a tiny gap between them, about 20 to 40 nanometers wide. To put that in perspective, a human hair is about 80,000 nanometers wide. The synaptic gap is roughly 2,000 times smaller than a hair. It's almost nothing, just a whisper of empty space. But that tiny gap is everything. It's where electrical signals become chemical signals, and then electrical signals again. It's where information gets passed from one neuron to the next. Every thought, every feeling, every memory, every moment of awareness, it all happens across these microscopic spaces. Here's how it works. An electrical signal travels down a neuron like electricity through a wire. When it reaches the end, it can't jump the gap. So the neuron releases neurotransmitters, those chemical messengers, into the synaptic space. These molecules drift across the gap in milliseconds, faster than you can blink. On the other side, the receiving neuron has special receptors, like locks waiting for keys. When the right neurotransmitter finds the right receptor, it fits perfectly. This triggers a new electrical signal in the receiving neuron, and the message continues on its journey. One neuron to the next, across gap after gap, building the networks that create your experience of being alive. The synapse isn't just a simple relay point though, it's more sophisticated than that. It can strengthen or weaken over time based on how often it's used. When two neurons fire together repeatedly, the connection between them gets stronger. The synapse becomes more efficient at passing messages. This is learning at its most fundamental level. Scientists have a phrase for this: neurons that fire together, wire together. It's the basic principle behind how your brain forms memories and learns new skills. The more you repeat something, the stronger the synaptic connections become, until the pathway is so well established that the action or thought becomes automatic. But synapses can also weaken. If a connection isn't used, if those two neurons stop firing together, the synapse gradually becomes less efficient. Eventually, it might disappear entirely. This is forgetting at a physical level. The pathway fades because it's no longer being maintained. Your brain has roughly 100 trillion synapses, 100 trillion microscopic gaps where chemistry and electricity meet to create consciousness. That's more connections than there are stars in 1,000 Milky Way galaxies, all contained in the space of your skull. And these synapses are constantly changing. Some getting stronger, some getting weaker, new ones forming, old ones fading away. Your brain is rewiring itself every single moment, adjusting these connections based on what you experience and what you pay attention to. Right now, as you read or hear these words, specific patterns of synaptic activity are lighting up across your brain. Neurons are firing, neurotransmitters are crossing gaps, electrical signals are racing along pathways. This is thinking, happening at a scale too small to see, but real enough to create the experience of understanding. And all of this happens in a brain that's mostly water. Here's something that might surprise you. Your brain, that 3-pound universe of neurons and synapses and electrical signals, is 73% water. Nearly 3/4 of your brain is liquid. You're carrying an ocean inside your skull. This isn't just water sitting there doing nothing. It's essential to everything your brain does. Water makes up the bulk of your brain cells themselves. It fills the spaces between cells. It's the medium through which nutrients travel and waste gets removed. Without enough water, your brain simply can't function properly. Even mild dehydration affects how you think. When you're just 2% dehydrated, something you might barely notice, your brain starts to struggle. Concentration becomes harder. Memory gets fuzzy. Reaction times slow down. Your brain needs that water to maintain the delicate balance of chemistry and electricity that creates consciousness. But there's another kind of fluid in your brain too. Cerebrospinal fluid. That clear liquid we talked about earlier when discussing the brain's cleaning system. This fluid surrounds your brain, cushioning it inside your skull. Your brain essentially floats in this protective bath, suspended and shielded from impacts. This is important because your brain is soft, fragile. Despite being the most complex structure we know of, it has the consistency of firm jello. If your brain weren't suspended in fluid, every movement of your head would jostle it against your skull. Walking, running, even just nodding your head would potentially damage it. The cerebrospinal fluid acts like a shock absorber. When you move suddenly, the fluid cushions the movement, protecting your brain from impact. It's elegant engineering, this liquid suspension system that keeps your brain safe while allowing you to move freely through the world. This fluid also helps regulate pressure inside your skull. Your brain is enclosed in bone, a rigid container that can't expand. The fluid helps maintain stable pressure even as blood flow changes, even as your brain swells slightly with increased activity. It's constantly circulating, being produced and absorbed, keeping everything balanced. And at night, as we discussed, this fluid takes on an additional role. It flows through your brain tissue, washing away the day's accumulated waste. Your brain's liquid nature makes this cleaning possible. The fluid can move through spaces between cells, carrying away debris, keeping your neural environment clean and healthy. Staying hydrated helps your brain in so many ways. It keeps your neurons functioning efficiently. It maintains blood flow, ensuring your brain gets the oxygen and nutrients it needs. It supports the production of neurotransmitters. It helps that cleaning system work properly during sleep. This is why drinking enough water is one of the simplest things you can do for brain health. Your ocean inside needs to stay full, needs to maintain its volume and composition. When you provide enough water, your brain rewards you with clearer thinking, better memory, improved mood. Right now, that ocean inside your skull is doing its quiet work, maintaining pressure, cushioning your brain, preparing for tonight's cleaning cycle. It's a reminder that you're not just neurons and electricity. You're water and chemistry, fluid and tissue, all working together in remarkable harmony. But this watery brain of yours has some surprising preferences. Your brain has preferences, and one of its strongest preferences is temperature. Your brain works best when it's cool. Not cold, but comfortably cool. And this preference shapes everything from how well you think to how easily you fall asleep. The ideal temperature for your brain is actually slightly lower than your core body temperature. Your body maintains an average temperature around 98.6 degrees Fahrenheit. But your brain functions optimally when it's a degree or two cooler than that. This is partly why your head has less insulation than the rest of your body, why you lose heat through your scalp so efficiently. When your brain gets too warm, everything slows down. Thinking becomes more difficult. Concentration wavers. You feel sluggish, foggy, less sharp. This is your brain trying to protect itself by reducing activity, creating less heat. It's like a computer that throttles down when it overheats. This is also why it's easier to sleep in a cool room. When you're ready for sleep, your body temperature naturally drops by a degree or two. This cooling signals to your brain that it's time to rest. It's part of your natural sleep preparation, your body's way of creating the conditions your brain prefers for sleep. If your room is too warm, falling asleep becomes harder. Your body struggles to achieve that natural temperature drop. Your brain doesn't get the signal that it's time to sleep. You lie awake, uncomfortable, your brain too warm to easily shift into sleep mode. The ideal sleeping temperature for most people is somewhere between 60 and 67 degrees Fahrenheit. That might feel quite cool, even cold, when you first get into bed. But once you're under covers, your body creates a warm microclimate while your head stays cool. This is perfect for your brain. Your extremities play a role too. Having warm hands and feet actually helps lower your core temperature. When your hands and feet are warm, blood vessels in them dilate, releasing heat from your body's core. This is why wearing socks to bed, despite seeming like it would make you warmer overall, can actually help you fall asleep faster. Your brain orchestrates all of this temperature regulation without your conscious input. It monitors temperature constantly, making tiny adjustments to blood flow, triggering sweating or shivering, directing your body to create or release heat as needed. It's another example of your brain's tireless background work. During sleep, your temperature regulation changes. In deep sleep, your body temperature drops to its lowest point of the 24-hour cycle. In REM sleep, when you're dreaming, temperature regulation actually pauses. Your body stops trying to maintain a specific temperature, allowing it to drift slightly based on the environment. This is one reason why extreme temperatures can disrupt your dreams. As you lie here now, your brain is already beginning its nightly temperature adjustment. It's signaling your body to cool down, preparing the conditions it prefers for sleep. Blood flow is shifting. Your hands and feet might feel slightly warmer as heat releases from your core. Your brain is creating its optimal environment. And as your brain cools, something peaceful begins to happen. Deep inside your brain, in a tiny cluster of cells, no bigger than a grain of rice, sits your internal clock. It's called the suprachiasmatic nucleus, and it's what tells your body when to wake up and when to sleep. This tiny structure keeps time for your entire body, conducting a daily rhythm that's been ticking since the day you were born. Your circadian rhythm, the roughly 24-hour cycle your body follows, is controlled by this cluster of cells. Even if you were locked in a room with no windows, no clocks, no way to tell day from night, this internal clock would keep running. You'd still feel sleepy at roughly the same time each night, still wake at roughly the same time each morning. But this clock isn't completely independent. It needs to stay synchronized with the outside world, and it does this primarily through light. Your eyes contain special cells that detect light levels and send that information directly to the suprachiasmatic nucleus. When these cells detect bright light, especially the blue light of morning sun, they tell your clock that it's daytime. When light fades, they signal that night is coming. This is why morning sunlight is so important for good sleep. It helps reset your internal clock, keeping it aligned with the actual day. And it's why bright lights late at night, especially the blue light from screens, can confuse your brain. Your internal clock receives mixed signals, thinks maybe it's still daytime, delays the production of sleep hormones. Melatonin is the main hormone involved in this process. As evening approaches, as light levels drop, your brain begins producing melatonin. This hormone doesn't put you to sleep directly, but it signals to your body that sleep time is approaching. It's like a gentle announcement, preparing all your systems for the transition to rest. Production of melatonin starts ramping up a few hours before your usual bedtime. It peaks in the middle of the night, then drops off toward morning. This rise and fall creates a biological tide that pulls you toward sleep and then back toward waking. It's remarkably consistent, following the same pattern night after night. But this rhythm affects more than just sleep. Your body temperature follows a circadian pattern, dropping at night and rising during the day. Your blood pressure follows its own cycle. Even your immune system works on a circadian schedule, with different functions being more or less active at different times of day. Your brain is essentially conducting a symphony of biological processes, each one timed to happen at the optimal moment in the daily cycle. Digestion works best at certain hours. Mental performance peaks at certain times. Physical strength follows its own rhythm. Everything is choreographed by that tiny cluster of timing cells. When this rhythm gets disrupted, you feel it. Jet lag is essentially your internal clock being out of sync with the external world. Shift work that constantly changes your schedule can leave your clock confused, never sure what time it really is. Even staying up too late on weekends can throw off your rhythm, making Monday mornings especially difficult. But right now, if you're reading this as evening turns to night, your internal clock is doing exactly what it's supposed to do. It's sensing the darkness, producing melatonin, lowering your body temperature, preparing every system for sleep. And right now, as you read this, your brain might be sending those sleep signals. We've traveled quite a distance together tonight, through forests of neurons and rivers of electricity, through chemical messages and microscopic gaps, through memories and emotions and the slow rhythm of sleep approaching. And we've arrived back where we started, at the brain that's experiencing all of this right now. Think about what your brain has done just in the time you've been reading or listening to this. It's maintained your breathing without you thinking about it, kept your heart beating steadily, processed these words, turned symbols or sounds into meaning. connected new information to things you already knew, all while preparing itself for sleep, adjusting temperature, releasing melatonin, shifting into slower brain waves. Your brain contains multitudes, 86 billion neurons, each connected to thousands of others, 100 trillion synapses where chemistry and electricity meet, regions specialized for memory, emotion, movement, sensation, planning, dreaming, all of it working together so seamlessly that you experience it as a single unified self. But your brain isn't just a collection of parts. It's not like a machine where you can point to one component and say, that's where consciousness lives, or that's the part that makes you you. Consciousness emerges from the whole system, from all those parts working together, creating something greater than the sum of their pieces. And here's what I find most profound about all of this. Your brain is trying to understand itself. The organ of understanding is turning its attention inward, studying its own nature. It's like a flame examining combustion, water studying fluidity. There's something almost magical about that, something that hints at depths we haven't fully explored yet. Scientists have learned so much about the brain in recent decades. We can map its structures, measure its electrical activity, identify which regions activate during different tasks. We understand neurotransmitters and synapses and plasticity. But we still can't fully explain how all of this creates the experience of being you. How 3 pounds of tissue produces consciousness, self-awareness, the feeling of existing in the world. Maybe that mystery is okay. Maybe not everything needs to be fully explained. There's beauty in standing at the edge of understanding, knowing both what we've learned and what remains unknown. What matters most right now is this. Your brain has carried you through today, and now it's ready to rest. It's preparing for its nightly maintenance. It's cleaning and organizing and processing. It's earned this rest, and so have you. As you drift off tonight, as your brain waves slow and your thoughts become dreams, trust the process. Your brain knows what to do. It's been doing this every night of your entire life. It will clean itself, process your memories, prepare you for tomorrow. All you have to do is let go and allow it to happen. Before you drift away completely, I have one gentle request. If this peaceful journey through your inner universe brought you calm, if these quiet discoveries helped ease you towards sleep, would you do something for me? Hit that like button. It's a small thing, just a tap, but it tells me these journeys matter to you. And then subscribe, because tomorrow night I'll be back with another exploration into the wonders that live quietly all around us. Tomorrow brings another journey. Maybe we'll drift through the cosmos. Maybe we'll explore the hidden world of the ocean. Maybe we'll discover something about time, or light, or the quiet physics of falling asleep. Whatever it is, it will be here waiting for you, ready to guide you gently toward rest. Sleep peacefully, knowing you carry such wonder within you. Good night.